Hello children, today we are going to discuss about Gauss law. We have already discussed about what is electric flux. What is electric flux? The number of lines of force passing through any area held normal to the surface is called electric flux. It is denoted by phi, and phi is equal to E dot ds. So after this flux was invented, there were so many experiments that were happening with regard to this, and the famous scientist Gauss put forth a law which is known as Gauss law. Okay, so we are going to discuss about Gauss law today. So this law states that the total electric flux passing through any closed surface. Electric flux means the number of field lines, right? Passing through any closed surface is equal to 1 by epsilon naught times the charge enclosed by the surface. That is, we know that flux is denoted by phi, right? Phi will be equal to passing through any closed surface will be equal to 1 by epsilon naught times the charge enclosed by the surface. Okay, it is not. So it is 1 by epsilon naught into Q. So this will be equal to Q by epsilon naught. We already have learned this in the previous class of electric flux. Phi is equal to E dot S. So now when the LHS are equal, when you equate the RHS, you will get E dot S will be equal to Q by epsilon naught. Okay. And you can see a diagram here. So this is the charge that is enclosed, and a spherical Gaussian surface is taken. Okay. Gaussian surface is nothing. S is Gaussian surface. Gaussian surface is an imaginary or hypothetical surface. It actually doesn't exist, but any shape which can enclose the charge and which can help us calculate the flux emerging from the charge can be taken as a Gaussian surface. And the point where you're going to calculate the electric field will be on the surface or away from the surface of this Gaussian surface. Okay. So here you can see that the electric field will be radiated radially outwards, and the area vector and the electric field vector are lying one over the another. So cos theta value will be equal to 0. The same thing will be true for all the Gaussian surface, all parts of the Gaussian surface, so that this law is valid for the surface enclosed within surface that is enclosing Q. So again, Gauss law states that the total flux lines passing through any closed surface is equal to Q by epsilon naught times the net charge enclosed by the surface. So now proof of Gauss law. You know that the electric flux through the surface is given by E dot S or E dot ds. And in the initial classes, we have studied the electric field as 1 by 4 pi epsilon naught Q upon R square, right? So what will be surface area of the sphere can be taken as 4 pi R square. So now what will be E dot S? We will calculate here. E dot S will be 1 by 4 pi epsilon naught Q by R square into 4 pi R square, right? So R square cancelled, 4 pi cancelled, you will get Q by epsilon naught. So E dot S is equal to Q by epsilon naught. This is what we wrote in the previous slide also. So now you understand that E dot S is equal to Q by epsilon naught, and this E dot S is pi. So pi is equal to Q by epsilon naught. This is what Gauss law says. Okay. And Gaussian surface is a hypothetical surface. Any hypothetical closed surface enclosing a charge is called the Gaussian surface of that charge. It can be depending upon the nature of the charge and where the charge is positioned. You can take a spherical surface, or you can say take a cylindrical surface, or you can take a cuboidal surface according to your convenience. Does the surface actually exist? No, it is an imaginary surface. Now coming to the important points, this Gauss theorem is valid only for closed surface. The shape can be any shape. And the charge distribution can be any distribution, that is line charge, volume charge, surface charge, or anything. This closed surface is an imaginary surface that should enclose the charge within. Okay, if the net charge enclosed by the closed surface is 0, that means if there is no charge inside the Gaussian surface, then the flux will also be equal to 0. And for example, imagine this is our Gaussian surface. There is a charge Q here. Will this contribute to the flux that is emerging, any flux that is emerging from the surface? No. Okay. So only the charge that is present inside should be taken into consideration. So the net flux through a closed surface due to a charge lying outside the closed surface is equal to 0. And this charge Q, pi is equal to Q by epsilon naught, right? This doesn't refer to a single charge. This refers to all the charges that are enclosed within the Gaussian surface. Okay, 4 points. Closed surface should be taken, and if there is no charge enclosed in the closed surface, flux is equal to 0, and any charge lying outside cannot contribute to the flux. And the charge Q, what you take is the sum of all the charges that are present inside the closed surface. With this, let us do some numericals to test our understanding quickly. Calculate the number of lines of force originating from a charge of 1 coulomb. Okay, so you are asked to calculate the number of lines of force. So you know that phi is equal to Q by epsilon naught. So Q is 1 coulomb, right? So 1 by 8.854 into 10 to the power minus 12. Okay, so if you solve this, you will get it as 1.129 into 10 to the power 11. So this is the number of lines of force that is originating from a charge of 1 coulomb. Number of lines of force. Okay. Now you can see here, I have taken the expression for flux, right? So what does this represent? Number of lines of force will be equal to the flux through a closed surface enclosing a charge. Okay. So that I will write it here. That is very important for you to understand. Number of originating from a charge will be equal to electric flux through a closed surface electric flux through a closed surface. Closed surface enclosing the charge. This concept you have to remember. Only then you can calculate the number of lines of force. Next question, a positive charge 17.7 microcoulomb is placed at the center of a hollow sphere. Radius is given 0.5 meter. You need to calculate the flux density through the surface of the sphere. Please understand, flux is different, flux density is different. So to calculate flux, phi is equal to Q by epsilon naught, right? Q is 17.7 microcoulomb. Micro means 10 power minus 6. That is your Q value. Epsilon naught is 8.85 into 10 power minus 12. So when you simplify this, you will get it as 17.7 and 8.85. It will be approximately equal to 2 into 10 to the power 6 Newton meter square per coulomb. We have discussed regarding the unit in the previous classes. Please go through. Now coming to flux density, but we are asked to find out flux density, right? We are not asked to find out flux. Flux density is equal to total flux by area. So the total flux we have calculated. Area, what is the surface given? Sphere, right? So area of the sphere is 4 pi r square. So radius is also given. So our work is easy. Total flux is 2 into 10 to the power 6. 4 into pi into 22 by 7 we can substitute into area is 0.5 square. When you simplify this, you will get it as 6.4 into 10 power 5 Newton per coulomb. Okay. Flux density is to be noted. If they ask you total flux upon the area, you have to calculate. Area is 4 pi r square for a sphere. Any other material, you have to use it appropriately. Okay. Then the last question, figure shows 5 charged lumps of plastic, and you also have electrically neutral coin. The cross section of a Gaussian surface, yes, is indicated. So what is the net electric flux through the surface? The values are given. Q1 is equal to, Q4 is equal to, Q2 is equal to, Q3 is equal, Q2 is equal to, Q5 is equal to, and Q3 is equal to. So now if you can see here, this neutral coin and the outside charges will not contribute to any flux. I have told you. Okay, so the charges inside will contribute to the flux. So phi will be equal to Q by epsilon naught. So you have to add this Q1, Q2 and Q3. So Q1, Q2 and Q3 means Q1 is 3.1 nanocoulomb. So nano means 10 power minus 9. Plus Q2. Q2 is minus 5.9 into 10 power minus 9. Then again plus Q3, right? Minus 3.1 into, that is also nanocoulomb. So it is minus 3.1 into 10 power minus 9. Divided by 8.85 into 10 power minus 12. So now when you simplify this, the answer will be minus 0.67 Newton meter square per coulomb. Okay. So now you have to simplify this and see, only then you will be able to understand this and get this answer. Please do it without fail. You already know that charges will follow algebraic addition. So whatever is plus you add, whatever is minus you add and subtract, and you get the magnitude of the resultant. That you have to be very careful. Okay, I hope you have understood the concept of Gauss law. With this only we can proceed to the applications of Gauss law. So if you have any doubt, you can raise in the comment section. We'll be happy to help you. Thank you.